Hello everyone. This video is a demonstration of how to simulate steady-state current by following this documentation. You should get this documentation in your hand if you read our paper. This doc provides a step-by-step guide on implementing the COMSOL model. The content is shown in the doc. The subtitles of the model implementation are the main steps. We also provide the mesh refinement model implementation, which will give you more accurate results. After you finish the tutorials, so you should get the results shown in here. So this is the steady state current without mesh refinement. And this is the steady state current calculated with the mesh refinement. You will see that this value is closer to the theoretical value calculated using limiting current equator, which listed in here. Let's go back to the model implementation and start implement our COMSOL model step by step. Let's start to build our COMSOL model. So first is the model wizard. You can click the model wizard in here, and then you will go to the space dimension window. So in this window, we will click the 2D XC metric button. Since we assume the electrode and the solution to be in the form of a cylinder, so 2D asymmetric is a good option. And then in the select physics tree, we will choose the chemical species transport and transport of dilute species TDS, and click the Add button. So in the Review Physics interface window, we will set the number of species is 2. And we hit Enter button. So you will see that the default concentration variable names C1 and C2. In here, we change it to COX, and the CRED, these two species, representing oxidized and reduced forms of species. So once the variable setting is done, and then we will click on the study. In here, we select the stationary study since the steady state current is stationary, and then we click done. After we finish the model wizard, you will see a window like this. The next step is the global definitions, and the first thing is the parameters. We'll load the model parameters from a text file, okay, and the parameters we set here can be used anywhere in this model because that is the global parameters. So let's do it step by step. In the model builder window, we will click on global definition and parameters. So in the setting windows, and here is setting windows, for parameters, we will click on load from file button. So load from file button. And then we'll just find out the parameter list, and it will load all the parameters. So actually I have written all of these parameters previously. You can just use those files. Otherwise, you'll have to hit enter and write whatever name and parameters you want in here. Now let's start build the geometry. So we will build the model geometry in this step. The 3D model geometry will look like the one shown in figure 1 in the main text. Since we choose 2D asymmetric model at the beginning, the geometry draw will be just 2D. First, let's build the electrode geometry. So we will right-click the geometry and then choose the rectangle. So the rectangle one will appear after the geometry, and then in the label, we can just type on electrode. In the label text field, this sets the geometry name as the electrode. In the size and the shape section, so we can type um, ELRAD, and for the height, it's ELRAD times 100. This sets the width and the height. So this ELRAD is the parameter, and we define it in our global definition parameters. So in here, that is our electrode radius, that is 5 micrometer. Okay, so let's go back. And then we can click on build all objects. So you will see a rectangle electrode will appear in the graphics window. This finish our electrode geometry. After we finish the electrode geometry, and then we will go to the glass geometry. So the same thing, we will click on right click geometry and find the rectangle. We name the geometry as glass in the label text field. In the size and shape section, so we will type RG ELRAD. And for the height is 100 times ELRAD. So the RG is also defined in the global definitions in the parameters. So we can see that the RG it's 50. That represents the ratio between the radius of the glass and the electrode. So let's go back to the glass. And right now we can build all objects. So this will show the glass geometry. After that, we will do our solution geometry. So solution geometry settings is nearly the same with the electrode and the glass geometry. And we will also right click the geometry and find the rectangle. So in the label text field, we can type solution to name this geometry. In the size and the shape section, we type 100 times ELRAD. For the height, it's 200 times ELRAD. In the position section, we can type negative 100 times ELRAD. Right now, we can build the object. So let's look at our geometry. To look at the whole field, we can just click the zoom. So you will see this big rectangle represents the solution, and here is the electrode, and this one will be the glass. Okay. So right now we finish our geometry, and let's start transport of dilute species. So in the model builder window, and we will find out transport of the dilute species here. And then we go to the settings window. And first we'll need to select the domain. And the domain we want to select is the 1. And we will need to click the 2 and remove it from the list, 3, and remove from selection. So the domain we select, you will see it's only the solution because the solution have the transport. And we will need to deselect this convection because we assume our system is the diffusion control. And you will see the equation becomes this. The first is the continuity equation. Second is the fixed first law. And then you can find out the dependent variables. It contains the concentration COX and the CRED. And those are the values we will solve for. And then we go to the transport properties. Okay. And for the transport properties, we will need to change the model input, the temperature, find out the user defined, and write TB. And for the diffusion coefficient, we set D for COX and D for CRED. So the D and the TB are the global parameters we select actually at the beginning. So we can just click find out the TB and the D, the diffusion coefficient in here. Okay. Now let's start to build our boundary condition. The first is the initial values. So for the initial values, because at the beginning, all the species is a OX species, the concentration will be the similar with the bulk concentration, which is type of CB. And for the RED species, they are all 0. And here we finish our initial value. And then we will right-click transport of dilute species, and we add concentration boundary condition. For this one, this is a semi-infinite boundary conditions, and is far from the electrode surface at that position. So these 2, 10, and 11. At that position, the COX will be the bulk concentration, CB, and the CRED, they are all 0. It's similar with our initial value. And then we need to do it again and add the concentration boundary condition. And we select species COX and species CRED. And for this boundary condition, we will select the electrode surface. So we can click on zoom box, zoom in this area to see the electrode surface we selected. That is the number 4. At this electrode surface, the COX becomes 0 and the CRED will becomes CB. And we simplified the situations. When we do the complicated like cyclic voltammetry and differential pulse voltammetry, in this electrode surface, we will use the Butler-Momo model, and we will set it later on. Let's start to build our mesh. And first we'll find out the mesh 1. And in the mesh 1, we go to the settings window, find out the mesh settings. And in here, we'll select user controlled mesh. Click it. And we go to the size. In here, we select the predefined normal. You can find other predefined element size in the list, but in here, the normal should be okay for our use. And we can build all. You will see the meshes has already built in our solution. Okay, but you will see that there is a problem for this mesh in our electrode surface. There's only one mesh that is not suitable for our use. So we will need to build more mesh at our electrode surface. So how to do that? So we will need to right-click the mesh 1, and in the more, we'll find out the edge. We'll need to move this edge up, and move it up, and select the electrode surface. And right-click the size. So in here, we will custom the element size and click on the maximum. In here, we select the maximum element size, ELRAD, divide 100. And we can click on build all. Right now, you will see the more mesh is built at the electrode surface. That is what we want. So we are done with the meshes 1 building. Right now, we are good for computation. We just go to the study 1 and click compute. Just wait for several seconds and we can get our results. So there is an error during the computation. We find out the error message in here. It's a time step. So we can go back to our settings. We'll find out the equation form is time dependent. So for our situation, it's a stationary, um, stationary state. So we will need to select the stationary, okay? And then the equation becomes this form. That's the equation form we will need to use for our calculation. And then we can go back to calculate again. Wait for several seconds. After finishing computation, a number of plots will be generated and listed in here. And we will also need to do more of the post analysis. So we can right click the derived values and select the integration and the line integration. So the line integration one will pop up below the derived values. And we select the electrode surface. Okay. And then we can load the values from the results line inted.txt files. Okay. We load these values. And of course, to get these values, this is the total flux at the z directions. You can also find out in here. Okay, I find out the component one transport of dilute species and species COX flux, and you will see the total flux will be in here. Okay. And right now, we can click on the evaluate. So you will see steady state current will show up.